Hello and welcome to this video from the course Number Theory, and in today's video we will study the concept of second principle of finite induction, and also we will see some examples. Okay, so we start with the concept of second principle of finite induction. In the last video we have studied the first principle of finite induction, or simply the principle of finite induction. Okay, the second principle of finite induction can be abbreviated as SPI, and the concept is that let S is any subset of set of natural number n having the following properties. Number one is that one must belongs to S, and the second is if k is an integer and such that whenever 1, 2 up to so on k belongs to S, this implies k plus 1 belongs to S, and if these two conditions are satisfied by a subset, then we see that this S must be equal to the complete set of natural numbers. Okay. Remark: before solving some examples, we write a remark that the second principle of finite induction looks stronger than first principle of induction, but these are equivalent. Okay, now we start with the example. Let a1 is equal to a2 is equal to 1, and we have the recurrence formula an is equal to an minus 1 plus an minus 2 for all n greater or equal to 3. So we have to prove that 2 to the raised power n minus 1 an is congruent to n mod 5 modulus 5 for all n greater or equal to n. Okay, a is congruent to b mod 5 means, or we can say that a is congruent to b mod 5 if and only if their difference is divisible by by 5. Okay, means two integers are congruent if and only if their difference is divisible by 5. Okay, now we move further. Consider for n is equal to 1, we can see that this condition p1 is satisfied or not. Instead of n in the formula here, in this formula, this is actually the condition which we want to prove. In this formula, instead of n we will put 1, so instead of n minus 1 it will be 0 when we will put 1 instead of 1 n. A1 is congruent to 1 mod 5. Okay, 2 to the power 0 is 1, so A1 is congruent to 1 mod 5, and since we know that A1 is equal to 1, this means P1 is true, or we can say that it is true for n is equal to 1. Now we move further. Okay, suppose Pn, which is 2n minus 1 an, is congruent to n mod 5, is true for all n is 1, 2 up to so on k. Now we have to show that p k plus 1 is true. Okay, now consider, we have to show that is true. Consider that a k plus 1 is equal to a k plus a k minus 1, because in the start the recurrence formula was given in this way, that a n is actually sum of the previous two terms. Okay, so a k plus 1 will be a k plus a k minus 1, and we multiply 2k both sides of this equation. We will get 2k a k plus 1, 2k a k plus 2 to raise power k a k minus 1. Okay, and this will be equal to, we just rearrange this 2k as 2k into 2 into 2k minus 1, because whenever we will add 1 and k minus 1 we will get a k 2 to raise power k, and then a k plus, we can write it as 2 square into 2 to raise power k minus 2 a k minus 1. Okay, we know that if we take the modulus, 2 k a k plus 1 will be congruent to k. Okay, before this we see that 2k minus 1 a k is congruent to k mod 5, and similarly 2k minus 2 a k minus 2 is congruent to k minus 1 mod 5, because we have assumed that this Pn is true for all n from 1 to n. So this is for n and this is for n minus 1. So these two are true. So if we apply modulus here, we will get 2 times k plus 2 square into k minus 1 mod 5. Okay, we will simplify further to get the result. Okay, this is 2k a k plus 1 is actually congruent to 6k minus 4. After simple calculation, 2k minus 2 square k minus 1 is actually equal to, we can say that plus is actually equal to 6k minus 4 mod 5, and after some rearrangement we can see this will be k is congruent to k plus 1 mod 5, because 6 is congruent to 1 mod 5 and minus 4 is also congruent to 1 mod 5, because 6 minus 1 is divisible by 5 and minus 4 minus 1 is also divisible by 5. Okay, now that is what we want to prove. Hence Pn is true for all n greater than equal to 1. Okay, we move to the second example. In this example, let A be any real number, then we show that the condition Pn is actually a to raised power n minus 1 is equal to a minus 1 into a to raised power n minus 1 plus a to raised power n minus 2 up to so on plus 1, and that is for all n greater or equal to 1. Clearly, P1, that is, if we take a to raised power 1 minus 1 is equal to a minus 1, is true for n is equal to 1. Okay, now suppose P1, P2 up to so on Pk are all true, that is a to raised power k minus 1 is equal to a minus 1 times a k minus 1 plus a k minus 2 plus so on plus a plus 1, and similarly a k minus 1 minus 1 is equal to a minus 1 into a k minus 2 plus a to raised power k minus 3 plus so on plus a plus 1. Okay, this is our supposition. Now we see that, now consider a to raised power k plus 1 minus 1, and that will be, if we add and subtract some terms, means we add ak and also subtract ak, and then we subtract a and add a for the balance minus 1. So we can easily see that left hand side is equal to right hand side, because we have added and subtracted the same terms, and after rearrangement it will be ak plus 1 plus ak minus a minus 1 minus ak plus a after some rearrangement. Okay, and if we take ak common, it will be a minus 1, and similarly if we take minus common, this will be a plus 1, and if we take a as a common from last two terms, it will be ak minus 1 minus 1. Okay, we move further. This will be equal to, on the right side it is a, on the left side ak plus 1 minus 1, and on the right side after some rearrangement it will be a plus 1 if we take, and the remaining terms will be a minus 1 into ak minus 1 plus so on plus a plus 1 minus a into a minus 1 up to so on ak minus 2 up to so on plus a plus 1, because instead of this term, and we have replaced this one, and if we take a minus 1 common here, it will be ak minus 1 minus a into a k minus 1 minus 1. And for this term we have added this one, so we get this expression, and after simplification we get a minus 1 into ak plus a k minus 1 plus so on plus a plus 1. What we have done, we have multiplied this a with every term of this and then rearrange. Okay, this a minus 1, and that is what we want to prove. Hence Pn is true for all n greater or equal to 1. Okay, now we have a remark. In this remark, the above example can also be solved using principle of finite induction or PFI, principle of finite induction. Okay, so that's all about this video, and we will see you in the next lecture. If video is interesting, then please subscribe the channel and like the video.